Hello all. So in this video, we'll learn about Gauss-Jordan with parameterization. In the last example, we learned about the technique called Gauss-Jordan for reducing a matrix to find the solution of a system of linear equations. That example was quite straightforward because we had a unique solution at the end. In this video, we will learn about the other two cases when we have infinitely many solutions. There we need to introduce parameters, and when we have no solution, on how to tell when we'll have no solution for a system. Before that, we need to understand two definitions: lead variables and free variables. And this works in the reduced row echelon form in the RREF. So you'll be given a system of linear equations. You'll set up the augmented matrix, and then you will look for each column, and each column that has a leading entry, also known as pivot, is called a leading variable. And for those columns that does not have a pivot or have a 0 in the leading entry, we call those variables free variable. It will be more clear once I solve an example. So these are the four rules to tell, or the steps to follow to see if a system is going to be consistent or inconsistent. So we first do Gaussian elimination on any system, and then this step, number 2, tells you that if there is a row such that 0 equals 1 or any non-zero number here, there will be no solutions for that given system. We will see an example later on, but you can just discard any system by saying it has no solution, and you don't have to go to the Gauss-Jordan method. Number 3 tells you if every variable has a pivot in its column, then there is exactly one solution. We solved a question like this in the last video. In today's video, I'll focus more on a system which has infinitely many solutions, or there will be columns which will not have a pivot. For these types of problems, for number 4, for systems which have more than one solution, we will need to introduce parameters for the free variables. To introduce parameters, we follow the following steps. So we need to do Gauss-Jordan elimination. This is to reduce calculation and unnecessary fractions, reduce fractions, and hassle at the end. Once you have done the Gauss-Jordan elimination and you know that you will need to introduce parameters, we will look for the free variables and will assign our parameters to the free variables. And again, then we turn the rows of the matrix into equations and substitute. Let's follow steps 3 to 5 in our next example. Like I said, if you go back to the last video, you will see when we are applying Gauss-Jordan, but we have a unique solution, so we don't need to do the parameter introduction. Okay, the first example that I have for you is a system which will have infinitely many solutions. So a typical question in exam or homework assignment or a web work assignment will look like this. You will be given a system of matrices. To reduce the length of this video, I've already given you a matrix which is in the REF form. So in the question, they will not exactly tell you how many solutions the system will have. It is your job to find out if the system is consistent, inconsistent, if it has a unique solution or many solutions. It will be your job to find out. For this case, I'm giving you a REF. So this matrix, as you can see, is already in the reduced echelon form, right? Row echelon form. Let's assign variables for this matrix. So this will be my x1, this will be x2, this will be x3, or you can assign any variable you feel like, x5, and this will be the right hand side, right? The column, the constants of our system. Now, Once I have my matrix, you can see that this matrix is already in your row echelon form, and you can immediately realize if I go from the upper left corner, I have a pivot, a non-zero entry in column 1. So that is definitely not my free variable. X1 is going to be lead variable. When I move on to X2, it doesn't have a pivot entry, right? It has a 0. And then I go to X3 and look, X3 has a non-zero entry. Then I move on to X4, it doesn't have a pivot. It has a 0 entry. Then I go to X5 and it has a non-zero 1. And I've explained this here also. We can see that the variables X1, X3, and X5 have a pivot entry, a non-zero pivot entry, whereas X2, X4 don't. Hence, using the definition from the beginning of this video, X1, X3, X5 are leading variables, and X2 and X4 are free. So once I know that this system is definitely going to have infinitely many solutions, I'm going to apply Gauss-Jordan to get the RREF. So I'm already at the Gauss elimination step, and I'm going to make everything above my leading ones 0. So I need to make, I start from here. I start from the last pivot entry, and I want to make everything above this corner 1 0. So I need to operate on row 1 and row 2. Now, how do I make the row 1 0? I add row 3 to it. How do I make the row 2 0? I add a multiple of 3 to row 2. And there you go. We have done this many times. When you go further in this course, you will learn many techniques on finding out if a system is going to have infinitely many solutions without without getting to the RREF form. But we'll discuss that for later. So I find the reduced row echelon form for the given augmented matrix. And once I'm done, this is going to be my matrix that I rewrite as a system of linear equations. So I take this system and I rewrite the equations. So I have x1, negative x2. Let me just introduce the variables here as well. x2, x3, x4, x5, and that's the right-hand side. I rewrite the variables, and you can tell just by looking at the variables that my x2 and x4 are free. So x2, x4 are free. So I'm going to, the next step is to assign parameters to the free variables. Now you can pick any variables you like. I picked t and s, which is pretty standard for this course. So I'm going to replace x2 by t, x4 by s, and I'm going to rewrite all the leading variables using the new parameters. And there you go. My x1 becomes negative 3 plus t plus s. I'm changing I'm moving everything to the right-hand side and isolating my x1. And this is it. This is my general solution for the given system of linear equations. Now, t and s could be any real numbers. T and s are any real number. You pick a value. If you pick any value of t or s, then you get a particular solution for the given system. You could pick t to be 0. You could substitute any real number for t and s and get a particular solution and get a particular solution, which is more useful when you go in higher calculus where they need to find particular solutions for differential equations. For example, if I pick t to be 0, s to be 0, then x1 would be negative 3, x2 would be 0, x3 would be -1, x4 would be 0, x5 would be -6. And so on. For different values of T and S, you will get different particular solutions. And hence, because there are infinite choices for T and S, there are infinitely many solutions. Okay, so now that we've handled this case, let's move on to the next possibility. So what if they give you a row echelon form of an augmented matrix corresponding to a linear system of equations, and you come across a row that looks like this. Now I want to put your focus on row 2 of this matrix. You see what is happening here? If I rewrite the given augmented matrix as a system of linear equations, as a system of equations, what do you see? You'll have a row, you'll have, let's assign the variables here. I have x1, x2, x3, and I'll have x1 plus 2, x2 plus 3, x3 equals 3. Well, nothing looks fishy there. Surely you can find values of x1, x2, x3 such that it equals to 3. Sure, nothing looks bad. How about the next one? So I convert the row 2 of my matrix into equations and I get 0 equals 7. Now this is weird, right? This is absurd. There's no way you can have 0 equals 7. Even if I write down the third equation, this will never hold. This is absurd, right? So whenever you come across a row like this, where you have 0 equals 0 on the left-hand side and non-zero on the right-hand side, keep in mind, this is one of its kind, right? That system will never have a solution because no x1, x2, x3 will make equation 2 satisfy. No x1, x2, x3 can make equation 2 hold, right? So there is no solution for the given system. There is no solution. For the corresponding system. And this is it. This is how you check if a system has no solution. Now, I just want to make sure that you understand the difference between two types, which could be very confusing, especially if you're in an exam. You might panic and rewrite that system as a no solution case. Well, that would be wrong. If I give you another equation, say I give you 1, 2, 3 equals 4, and I have 0, 1, 1 equals 0, and then I have 0, 0, 2 equals, say, something 3, right? I have x2 plus x3 equals 0. This system could have solutions, right? Or even if I make this, let's say, okay? When I rewrite the system, when I rewrite equations for this, just to distinguish between the two cases, which are very similar, but not quite. So I have 2x2 plus 3x3 equals 4, and I have x3 equals 0, which is very valid, right? And I have 2x3. Oh, this didn't make sense. Never mind. So I should not make examples as we go, right? Let's just make this 1, make this 2. And then I have 2x2 plus x3 equals 3. And if you come across a similar system in exam or in a homework, just note that this is completely fine, right? This is okay. My variable could be 0. This system will have solutions. If not one, many, but this is not a no solution case. And this is it for today's video. See you in the next one.